Thank you. Alright, so welcome to, I don't know which week this is, some week. Okay, so let's do a quick recap, right? So we have been talking about tight cuts. So a tight cut is any cut that meets every perfect matching of the graph exactly once, right? And we have seen two types of tight cuts. They are actually important, as you will see throughout this course. They are barrier cuts. So you have a barrier, and when you delete the vertices of the barrier, you get equal number of odd components. And observe that for every odd component, the corresponding cut is a tight cut. Of course, it could be trivial if the odd component is just a single vertex. Okay, so these are barrier cuts. And then we have two suppression cuts, where you have a pair of two vertices that comprise a two vertex cut that is not a barrier. So a two suppression is a two vertex cut that is not a barrier. So therefore it follows that all the components you get will actually be even components, right? Two or more. So what you do is you put one or more even components here and one or more even components here, disjoint, and you consider this cut or symmetrically this cut, and observe that these are also tight cuts. Right? Hopefully you all have convinced yourself by now that these are indeed tight cuts, right? Okay. So here's an example, here's a concrete example of a two suppression cut, and here is a concrete example of a barrier cut. Yeah. Okay. So yeah, we are continuing with the tight cut decomposition theory, and one important component is what are those matching covered graphs that do not have tight cuts, non-trivial tight cuts, right? Every matching covered graph has trivial tight cuts. Those are unavoidable. They are trivial cuts are tight by definition of perfect matching. So what is interesting is, of course, non-trivial tight cuts. So matching covered graphs that are devoid, or if you like, free of non-trivial tight cuts. These are called bricks and braces. The bricks are the non-bipartite creatures, and braces are the bipartite creatures. Typically you would say braces and bricks, bipartite first, non-bipartite next, but that doesn't sound as nice as bricks and braces. So we say bricks and braces. Yeah. And people have often asked me, why are the bipartite ones called braces? Shouldn't the bipartite ones be called bricks and the non-bipartite ones be called braces? Well, here is an explanation. If you look up the word brace in the dictionary, it has something to do with something that comes as a pair. So bipartite graph comes as a pair, white vertices and black vertices. So brace has something to do with pairing or pair. You can read more about it. Okay. So this is one way to remember why braces are bipartite, whereas bricks are the non-bipartite ones. Okay. Alright, anyways, that's just terminology. But now let's try to figure out some properties of bricks and braces. The other unfortunate thing is, if I want to talk about properties of bricks and braces both, I have to say bricks and braces. There's no common word for both of them together. Sometimes I call them indecomposable matching covered graphs, but it's just long. Bricks and braces are actually shorter. So let's try to figure out some properties of bricks and braces based on our earlier discussion. So can you all think about it? Any non-trivial barrier any or some of them at least, would give you a non-trivial tight cut. Not always, but yeah, you need some condition. And if you have a two separation, then definitely you will get a non-trivial tight cut. Right? The way we define two separation cut, it is always non-trivial. So let's look at that first. Can we talk about connectivity? Naturally, one of the most fundamental properties is connectivity. So what do you think we can say about bricks and braces based on the fact that barriers and two separations will probably result in non-trivial tight cuts, probably. So yeah, think about it, and if you have a guess, raise your hand. There may be some small exceptions. So small exceptions are always there in life. Well, most of the time they're there. Anyone else? Yeah, so if you have figured out some property, try to see if you can also figure out the exceptions. Generally the exceptions will be on small number of vertices. Let us recall that all matching covered graphs except K2 are two connected. Right? That we know. We know that matching covered graphs except K2 are two connected. So anyone else? Can we say something stronger about bricks and braces? Figured out the exceptions. Yeah, okay.
We are not three connected.
Not three connected? Or should be three connected? Which one?
Not three connected because I think K4, no, C4. C4.
Yeah, so minor exceptions could be there. What about bigger ones? Figured out the exceptions. Okay, see if you can figure out the exceptions. Yeah, okay. So can there be a two vertex cut? Let's try to figure that out. Supposing there is a two vertex cut, I delete these two vertices and now my graph disconnects. Well, the components will either be odd components or even components. If there is an even component, then there is another even component. Yeah. There could be more even components. And this is a problem, right? Because bricks and braces are supposed to be not having any non-trivial tight cuts. Right?
Why two even components?
There will be at least two, right? So let's recall the definition of two separation cut. You can get any number of even components. There could be 100 even components. I'll put 49 here, I'll put 51 here. This is a tight cut. And it is non-trivial. Right? So if I get two or more even components, I have a non-trivial tight cut. Right? And that is a contradiction because bricks and braces do not have non-trivial tight cuts. Right? So if you delete two vertices, you definitely should not get even components. That is clear? Yeah. So you can't get even components. So the only other possibility is you get odd components. But now if you get a non-trivial odd component, because there is at least two vertices here, it's a two vertex cut, then I have a non-trivial tight cut again. So therefore if I delete two vertices and I get odd components, my odd component should be trivial. That is just C4 up to multiple edges. Right? So, the moment you have 6 or more vertices, bricks and braces are 3 connected. Right? In fact, we can write a more concrete statement. Bricks and braces are 3 connected except K2, C2. The moment I have 3 edges, it is again 3 connected. We are using SGT definitions, right? Internally disjoint paths. So if I put 3 edges, this is 3 connected. Yeah. And the only other exception is C4. No matter how many multiple edges you add in C4, it will not be 3 connected. It will always have a 2 vertex cut. So you use the pessimistic viewpoint of connectivity, right? So those are the only exceptions in life. Every other brick and brace is 3 connected. Yeah? Okay? But of course, it is not true that 3 connected matching covered graphs are bricks and braces. That is a false statement. Here is a counterexample. That graph is 3 connected. It is not a brick or a brace. It's only one direction. Okay? So there is more to it than connectivity. Okay. So I'm going to give some TIYs, well, maybe DIYs. So we have already characterized tight cuts in bipartite graphs. You all agree? We have already characterized tight cuts in bipartite graphs. What are braces? Braces are bipartite matching covered graphs that do not have non-trivial tight cuts. So therefore, you should be able to characterize braces in at least one other way using the tight cut characterization of bipartite matching covered graphs. Right? So that is a DIY. Characterize or find and establish alternative using the characterization of tight cuts in bipartite matching covered graphs. Yeah, we will discuss it later in a couple of lectures, but hopefully if you all think about it, you will automatically see some 2 or 3 different characterizations. They are all basically equivalent, and they are very useful. Okay, so braces are fine, and the reason they are fine is because we have a complete characterization of tight cuts in bipartite matching covered graphs. Unfortunately, we haven't discussed such a characterization in the case of bricks, in the case of general matching covered graphs, right? So it's not immediately clear how you get characterization of bricks using the information we have thus far in this course. Yeah. So let's try to focus on bricks. We will come to braces later. Let's continue thinking about bricks. So we know bricks are 3 connected. Observe that the only exceptions are actually all bipartite. So bricks are 3 connected. Yeah, everybody agrees. What else can we say about bricks? So 3 connected we got by thinking about 2 vertex cuts, which will either be 2 separation cuts or there will be barriers of cardinality too, right? But of course, even larger barriers could give you non-trivial tight cuts, right? So can a brick have a large barrier? By large I mean, okay, 2 vertices already not possible because it's 3 connected. Can a brick have a barrier of cardinality 3 or more? Supposing I have a brick and I have a barrier with 3 vertices, for example. So we get some odd components. These odd components may be trivial or non-trivial, single vertex or more. So in which case do we get a contradiction? Non-trivial. The moment you have a non-trivial odd component, you have a contradiction. You will get a tight cut. You will get a non-trivial tight cut. So the only option is to have all components be trivial. Okay? All components are trivial. Then the graph is bipartite. Yeah? Contradiction to brick. We started with the brick. Yeah? So what have we proved?
Maximal barrier is of cardinality 1.
Maximal barrier, or for that matter any non-empty barrier, is cardinality 1. Yeah? Yeah. You just cannot have non-trivial barriers. Oh, but not having non-trivial barriers, it's reminiscent of something, right? We saw that a graph is if bicritical, right? So therefore what we just proved is that bricks are 3 connected and bicritical. What we haven't proved is the converse. It turns out that bicritical 3 connected graphs are exactly the bricks. That is much harder to prove, and we will prove it soon in this course. Right? So what we have proved is brick implies 3 connected and bicritical. It turns out that the converse is also true. In fact, if you look at papers from the 70s and 80s, they used to define brick as a 3 connected bicritical graph, and they used to talk about some procedure called the brick decomposition procedure, which was basically just barrier cuts and 2 suppression cuts. Later people realized that 3 connected bicritical graphs are exactly all matching covered graphs that are non-bipartite and free of non-trivial tight cuts. So this was a realization people had much later. This was basically in 1982, Edmonds, Lovász and Pulleyblank proved that these are actually the same creatures. Right? So in fact, the converse holds, and it is a deep result due to Edmonds, Lovász, Pulleyblank, 1982. Yeah. Okay. And yeah, so that is one way to think of the Edmonds, Lovász, Pulleyblank result. The other way to think of the Edmonds, Lovász, Pulleyblank result, these are equivalent. So I'll give you a DIY to show that they are equivalent. So this is the ELP theorem. This is another way to state it. Whenever there is a non-trivial tight cut, there will either be a barrier cut or a 2 suppression cut. That is also non-trivial. Right? Every matching covered graph that has a non-trivial tight cut has one, so it has a non-trivial tight cut that is either a barrier cut or a 2 suppression cut. Okay, and this is the one we will see a proof of, and the fact that this is equivalent to this is a DIY. So star and I don't know, star star.
where you are taking a barrier of length 3. From here you are saying that there is no barrier of cardinality strictly greater than 1, because in that case we are getting bipartite.
That's right. Yes.
So here we also conclude that there is no barrier of cardinality 2 as well.
That's right. That's Even for cardinality 2, you can use the same argument.
You are specifically taking the barrier of size 3. So
No, 2 or more will work. Yeah, I did not take 2 just because you had already proved it is 3 connected. So barrier of cardinality 2 would already contradict the 3 connected thing that we established earlier. So that is why I took 3 or more vertices. But yes, same argument works for 2 also. Yeah. Okay, so these are 2 ways of stating the ELP theorem, either in terms of non-trivial tight cuts or directly as a characterization of bricks. Bricks are precisely the 3 connected bicritical graphs, and both of these statements are equivalent. Okay, good. So since we are talking about bricks and braces, let's also talk about some examples, right? It may seem that maybe they are very specialized, matching covered graphs, plus there is no non-trivial tight cut. So let's talk about some rich families of bricks and braces. Yeah. Okay. Maybe I'll get rid of these things. So, on assignment 5 of SGT, you proved that 2 connected cubic graphs are matching covered. This is actually a result of Schoenberger, 1934. Every 2 connected, 3 regular. I will generally say cubic instead of 3 regular. Graph is matching covered. Yeah. But such a graph may not be a brick or a brace. For example, a graph that I just erased this is a 2 connected 3 regular graph, but it is not a brick or a brace, right? Because it has a non-trivial tight cut. Okay. Observe that it is also a 3 cut. It has exactly 3 edges. Turns out that in a cubic graph, by that I mean 2 connected cubic graph, of course, every tight cut is actually a 3 cut. Okay, this will be a exercise to prove. Some of you may have already seen proof of it, but it may be one of the assignment problems for some of you. So here is a TIY. This is non-trivial. In a 2 connected cubic graph, every tight cut is a 3 cut. Okay. We haven't discussed all of the results that are generally necessary to prove this. So let me give you a weaker statement. The weaker version is bipartite. Okay, so this is a DIY. Prove the above for bipartite graphs. It's easier because for bipartite graphs we have a complete characterization of tight cuts. Right? all tight cuts are barrier cuts, and there is a nice majority minority structure that we discussed last week. So using that and using simple counting arguments, you can prove that in bipartite cubic graphs, tight cuts are going to be 3 cuts. Okay. Okay. So that means if a bipartite graph, cubic bipartite graph, does not have non-trivial 3 cuts, then what does that mean? What does that imply? If I have a connected cubic bipartite graph, by the way, connected implies 2 connected, fun fact. If I have a connected bipartite cubic graph and I say that it doesn't have any non-trivial 3 cuts, then what does it mean? Then it is a brace. Because if it has no non-trivial 3 cuts, then it has no non-trivial tight cuts, because every tight cut is a 3 cut. Therefore, it means that it is a brace. So in fact, here is a corollary. A 2 connected cubic graph, 2 connected cubic, okay, I don't need 2 connected because connected implies 2 connected. A connected bipartite cubic graph is a brace. This would imply rather we discuss the opposite. Let's see, is free of non-trivial 3 cuts. If it is free of non-trivial 3 cuts, then it is a brace. Turns out it is if and only if. So if and only if it is a brace. No, so connected and cubic and bipartite all together actually imply 2 connected. So that's another DIY. DIY. If G is a bipartite cubic graph, then connected actually implies 2 connected. I learned this quite recently while working with Santosh. I mean, I should have observed it much earlier, but for some reason I hadn't. Or maybe I had forgotten, I don't know. Very easy to prove, not difficult. Okay, is that correct? Yeah? No mistakes? Okay, good. So let's look at an example just to get some sense of the statement. So here is a nice graph. Here is a bipartite graph. And observe that this is a non-trivial 3 cut. And it is also, therefore, well, in this example you can check easily, it is also a tight cut. If you take all the 3 edges in a perfect matching, then you can't complete the perfect matching to a perfect matching. Right? So this is a non-trivial 3 cut, it's also a tight cut, and the statement is basically saying this, that if you don't have non-trivial 3 cuts, then you won't have non-trivial tight cuts also. Then these are equivalent to each other. Right? So let's introduce one terminology, because this is going to come up quite often. For a cubic graph to be free of non-trivial 3 cuts, we will call it essentially 4-edge connected. Of course, a cubic graph cannot be 4-edge connected because it has trivial 3 cuts. Right? But if the trivial 3 cuts are the only 3 cuts, then we will call it essentially 4-edge connected. Is that okay? So this is a definition only for I will include 2 connected in the definition. A 2 connected cubic graph free of non-trivial 3 cuts is called essentially 4 edge connected. Is it okay? 2 connected cubic graph that is free of non-trivial 3 cuts. It is called essentially 4 edge connected. Yeah. So another way to state this, for a connected cubic bipartite graph, it is a brace if and only if it is essentially 4 edge connected. Okay? Alright. And in fact, if you prove the first TIY, which is harder, then you can make the same statement. You can make a similar statement about all 2 connected cubic graphs. If you have a 2 connected cubic graph that is essentially 4 edge connected, then it has to be if you have a 2 connected cubic graph that is essentially 4 edge connected, then it has to be a brace or a brick. Yeah. Okay. So a corollary of the first TIY every essentially 4 edge connected cubic graph is a brick or a brace. Okay, so this is just a 2 connected cubic graph where there are no non-trivial 3 cuts. The only 3 cuts are the trivial ones, 3 edges incident at a vertex. Yeah. So if you don't have this, then your graph is a brick or a brace. Right? So now let's look at some concrete families using this. Yeah? And these families will play an important role in the future parts of this course, so it is a good idea to talk about them now. So, maybe I'll just call it families. Maybe the right title would be some important families of bricks and braces, right? So the first family is basically, you all know the prism, the triangular prism. Here is another drawing of the triangular prism. Yeah, this is C6 bar. Is this essentially 4 edge connected?
4 edge connected.
Yes, essentially 4 edge connected. So it should not have a non-trivial 3 cut. Or do you see a non-trivial 3 cut?
Yeah.
Right?
Yeah.
Everybody sees a non-trivial 3 cut. So this is not essentially 4 edge connected. Because these 3 edges joining the 2 triangles, they form a non-trivial 3 cut. But this is still a brick. This is still a brick. This is not an if and only if statement. Right? This statement is not if and only if. But now let's generalize this. Instead of a 3 cycle and a 3 cycle, I will take a 4 cycle and a 4 cycle. or I can take a 5 cycle into 5 cycle. These are all essentially 4-edge connected. Not difficult to prove, you can try proving it yourself. These are called the prisms. Prisms are 2 cycles of equal length joined by a perfect matching in the natural fashion to get a planar graph. Okay. And these are all, except for the first one, these are essentially 4-edge connected cubic graphs, and they alternate between being braces and bricks. Brace, brick, brace, brick. Yeah. So these are called the prisms. Right. Okay. Prisms are closely related to some other families. This is another way to draw prisms. Here is another way to draw prisms. Yeah. Yeah, these are also the prisms. But now what we'll do is we will make a twist, a Mobius type of twist. So instead of adding these 2 edges, I will add these 2 edges. Likewise here. Instead of adding these 2 edges, I'll add these 2 edges. These are all essentially 4-edge connected cubic graphs. And now you can see this fellow is actually bipartite. Anybody knows what this graph is? Yeah? If you have figured it out, raise your hand. If you haven't figured it out, that's okay. Figured it out? Okay, 1. Okay, fine. You could have raised your hand. Okay, so this is K33. This one is bipartite. This one is actually non-bipartite. This is called the Mobius ladder on 8 vertices. It is also famously called the Wagner graph, and so on. Yeah? So this is bipartite, this is non-bipartite, and then it keeps alternating, bipartite, non-bipartite. Okay? So these are the Mobius ladders. Yeah? And the prisms are also sometimes called circular ladders. But yeah, we'll probably stick to prisms. So these are 2 families of essentially 4-edge connected cubic bricks and braces. The only exception to essentially 4-edge connected is the smallest prism. Yeah. Peterson graph, essentially 4-edge connected cubic graph. We will use this for the Peterson graph because we will be seeing the Peterson graph very frequently in this course. Right, so this is essentially 4-edge connected cubic graph. Clearly it is not bipartite, therefore this is a brick. Right. Okay. Alright, so these are the essentially 4-edge connected cubic families I wanted to tell you about. But there are other interesting families which will play a role later. So maybe I'll just tell you about some of the families since we are talking about them anyways. What is an important family of three connected graphs that you see in SGT? Wheels, yeah? Tutt's wheel theorem. Yeah, everybody remembers that? So of course wheels can have odd number of vertices, we throw them out. In this course when we say wheel, we mean wheels with even number of vertices. And they are generally called odd wheels. Okay, fine. K4 is the smallest one. W5 is the next one. Then you have W7. So this is one of those odd cases where you use n minus 1 as a subscript rather than n. Yeah. Wheels are bricks. Clearly they are three connected, and you can also check that they are bicritical. If you check these two things, then it follows that they are bricks because of the ELP theorem. They can't have any non-trivial tight cut. Right. Okay. But if you have non-bipartite creatures, you should also have analogous bipartite creatures. So we have the bi-wheels. Right. So what are the bi-wheels? So it's like a wheel, but the bi should mean something, right? So it's a wheel with two hubs, a black hub and a white hub. The black hub joins to the white vertices, the white hub joins to the black vertices. So I have an even cycle. Color the vertices, solid and hollow, or black and white, whatever you like. Put a hollow hub, join it to solid vertices, put a solid hub and join it to hollow vertices. This graph is actually isomorphic to something you know very well. Anybody knows what that graph is? You can raise your hand and just signal to me. The smallest bi-wheel is actually a famous graph. Okay, I got it. Anybody else? So it's actually a famous graph and it's already drawn on the board. Now it is very easy. Now you can just check the order or something. Yeah, figured it out? Then there is a non-trivial tight cut that is either a barrier cut or a suppression cut.
That may not be the same.
No, it may not be the same. Yes, there will be some, yeah, it may not be the same. Yeah. Okay, anybody else? Everybody figured it out? Yeah? Yeah, everybody sees it? Right, it's the cube graph. Right? So that's the smallest bi-wheel. But there are more bi-wheels. Actually, there is a bi-wheel smaller than this. Is that correct? No, no, that is not a brace. Yeah, because that will be degree 2. Okay, fine. Okay, so this is the smallest bi-wheel. And then of course you can keep doing the same. Instead of 6 cycle, you take 8 cycle, you take 10 cycle, and these are all braces. Wheels are bricks. Yeah. Okay. Observe that wheels and biwheels are not cubic. They have 1 or 2 high degree vertices respectively, except for the cube.
We have anything like W7 for biwheel? Notation also.
Oh, for notation for biwheels. I think Lucchesi Murthy probably use biwheel of order 8, most likely. I don't think you subtract 2. Yeah, I don't think you subtract the hubs. That is only for wheel. That is because everybody uses that notation for wheel, so we subtract 1. But I think for biwheels, they use this notation for the cube, I think. Well, these are non-standard, so different papers might have different notation or they may skip it altogether. Yeah. But now that we have talked about wheels and biwheels, let's talk about another family of bricks that is related to biwheels. So what is a biwheel? Another way to think of a biwheel is to take a cycle. For example, I can take a 6 cycle. Let me color the vertices. And now I put one white vertex, one black vertex, or whatever, hollow solid. I join this to these. I join this to these. This is one way to draw a biwheel. Yeah, everybody agrees? It's the same graph as this graph. Okay? So what we'll do is we'll modify this slightly to get another family. We will remove this edge and replace it by these 2 edges. Observe that this is non-bipartite. These are called truncated biwheels. And these will also play an important role later. Right? So all of these families, we will at some point in this course discuss a theorem similar to Tutt's wheel theorem. One for bricks, one for braces. And when we discuss those results, these families will show up there. Right? So that is one reason I'm telling you about these specific families. They are not arbitrary. They actually play a role in the theory. So what do we have? We have prisms, we have Mobius sliders, we have wheels, we have biwheels, we have truncated biwheels. Okay, only one family is missing now. They are called the staircases. Right? They are cubic, but they are not essentially 4-edge connected. So here is the last family. So for this family, I will draw the prism like this. Yeah, this is a triangular prism. Now what you do is, you take these 2 edges, subdivide them by some number of vertices, equal number, and you join this perfect matching. So this is the staircase on 10 vertices. ST10 if you like. I don't think there is a standard notation again, but yeah. And the staircase on 8 vertices is actually a very important graph in matching covered graphs theory. This one has a special name. It's called the bicon. Right? If you talk to Shalu, she'll tell you about bicon all the time. So bicon is a very important graph. It comes up in different results in matching theory. Yeah, so this is generally this is called the smallest staircase. In fact, there is a fun story. So there is bicon. Okay, if I want to tell you the story, I have to justify the definition of bicon in a different way. Okay, so let's use splicing to understand some of these graphs. Then I can tell you the story. Supposing I start with K4 and I want to get the prism, what should I do? The operation you're allowed is splicing.
Triangular prism.
Yes, I want to get triangular prism from K4. So what should I do? I want to do splicing. What should I splice with? K4 with K4. K4 splice with K4 gives you the triangular prism. Okay. So here is K4 and you splice with K4 at any vertex. Of course, all vertices are the same. You will get the triangular prism. Yeah? Okay. So if you splice at one vertex of K4, you will get the triangular prism. What if you splice at two vertices of K4? Again with K4. So take K4, splice here with K4 and splice here with K4. What will you get? You can make a drawing and figure it out. It is drawn on the board. If you have figured it out, let me know, raise your hand and I'll come and talk to you. And if you have figured it out, also try 3 vertices of K4. Splice with K4 at 3 of the vertices with K4 again. Then what do you get? That graph is not drawn on the board.
How you are slicing with 2 vertices?
No, at splicing at 2 different vertices. Right, so let's do it. Let's do an example. Supposing I splice at this vertex. That is the same as this graph, right? If I splice at this vertex. If I splice at 2 vertices, so let's do this and this. So basically replace the vertex by a triangle and replace this vertex by a triangle. I'm going to splice with K4 only, right? So I will get a triangle here. I'll get a triangle here. This will remain as it is. Yeah? And now what do I get? Observe that I get this. I first splice with K4 here, then I splice with K4 here. I did it in one step. And you get this graph. And this is? Everybody figured it out? Yeah? Yeah? Figured it out? Bicon? Yeah? Yeah? Okay. Fine. So this is bicon. And if you splice at 3 vertices of K4, then you get another nice graph which plays a role in the theory again. Not as important as some of these families. Well, that's debatable. You'll get this graph. If you splice K4 at 3 vertices with K4, then you'll get this fellow. This is called the tricon. So the name bicon and tricon, they have actually appeared in the literature in multiple papers, starting from 2000s, mostly in Carvalho Lucchesi Murthy papers. Right. So how is bicon obtained? You take K4 and splice 2 vertices with K4. Splice at K4 with K4 at 2 vertices. For tricon, you splice with K4 at 3 vertices. So therefore, if you splice only at one vertex, what should that graph be called? It should be called unicorn. Right? If you splice at only one vertex with K4, you should call that graph the unicorn. So actually, Claudio wanted to call this graph the unicorn. But Professor Murthy was like, no, we can't do that. Unicorn is too much. So this should be called the unicorn. But we don't call it the unicorn, we just call it C6 bar, also known as a triangular prism. Right? So anyway, so that's a fun story about naming graphs. Yeah, anyways. Okay, so that's some families of bricks and braces. And what we will see in the future, quite far in the future, I don't know if we will have time to prove these theorems, but it turns out that all bricks and braces can be generated from these bricks and braces using some operations, similar to how all simple three-connected graphs can be generated from the wheels using some operations in the same sense. And in fact, even the proofs of these results, at least the proofs that were given by Carola Lucchesi-Murti, are very similar to how we prove Tutt's wheel theorem in SGT, except that they are much harder and much more complicated. But the essence is the same actually. If you have understood Tutt's wheel theorem and its proof well enough, then essentially if I give you the result, you can spend 6 months to a year and prove it. Yeah. Okay, so that's all for part 1, and we can take a short 5-minute break and continue to part 2. Are there any questions or concerns? Right, so next part we'll talk about the tight cut decompositions. Right? Enough of bricks and braces. Yeah. Thank you.